All right, so chapter 10 is a chapter, we're going to be doing a few parts of it, not all of it, but chapter 10 is really about conic sections, right? Chapter 10 is about conic sections. And so let's start our first lesson with a look at what are conic sections. I know the first time I heard about conic sections, I was like, I don't know what this is, but it seems like it should be pretty scary because the name feels like really grown up. But it turns out that conic sections are nothing more than sections of a cone, right? So conic sections mean sections of a cone. And we can almost replace this word sections with slices of a cone. All right. So when we talk about conic sections, we're really looking at slices of a cone. All right. And in fact, we're going to be looking at slices of not just one cone, but ones that are generated by two cones. And here's what that is going to look like. Okay. So the way I draw these, I sort of draw like a ovally situation. And then I'm going to draw the same ovally situation, whoa, but down here. Okay. And then I'm going to connect this top left corner with the bottom right corner with a straight line. And then I'm going to connect the top right corner with the bottom left corner with a nice straight line. And we can see that we have sort of these two cones stacked on top of each other. All right. I don't know how many of you know what an hourglass is, but this might sort of look like an hourglass shape, right? Hourglasses usually have like sand inside of them, and the sand, like when you turn them over, sand goes into the bottom part of it, and it's called an hourglass because it takes an hour for the sand to go, like all of the sand that's up here to go into the bottom. But we're going to be taking a look at like, what are the different ways that we can slice this shape and think about four special kinds of sections, okay? And so what we're going to do, I'm going to cheat a little bit. I'm going to go ahead and copy this diagram into each of the four spots that I have here. Right, so you'll notice that you have enough space to draw those cones 4 different times. So I'll give you a moment to do that. And then we're going to talk about the 4 conic sections that we're going to be looking at. Okay, we're going to look at as many of them as we can today, and whatever we don't talk about today, we will finish up on Monday. Okay. So we're going to start with the first conic section. And instead of giving it a name right away, I'm going to draw some slices, and I want you to tell me what you think the name is. Okay. So let's say that I cut right through the cone like this. And in particular, I'm cutting, so the slice is parallel to the base, right? So I'm making a slice that is parallel to the base. And I could make one like up here, that's parallel to that base. Could make one maybe down here, that would be parallel to that base. And all of these slices, turns out, as Dallas says, are circles. How many of you in here enjoy ice cream? And in particular, an ice cream out of a ice cream cone? Of course, okay. So if you think about an ice cream cone, right? When you look at the top of your ice cream cone, where the pointy part is at the bottom and you look at the top, that's a circle, right? And so that's exactly what we're saying here is that when we slice parallel to the base, right? When we hold our face directly over that ice cream cone, we notice that each cross section is like a circle. Okay. Now, let's imagine that instead of cutting straight across, you have slices that are not parallel to the base and does not cut through the base. Okay. Meaning, what if I cut something like that? Would that still give me a circle? All right, that's it. That's a good guess. No, that does not give us a circle. What do we think this might generate? Yeah, exactly. So these are ellipses, okay? And one might think of them as ovals. Oval is probably a more familiar word for us than ellipse. Ellipse sounds very grown up, but an ellipse is basically a slanted circle or an oval, okay? And so that's what you looked at on Desmos before class today. Now, we're going to talk about those today. We're going to talk about like, how do we graph them? How do we know from the equation that it's going to be an ellipse or a circle? But we are also going to talk about a few other conic sections, 2 more in fact, okay? And so we're going to be looking at ones where slices are not parallel to the bases and they do cut through the base. Okay, so for example, maybe something like this. If I cut the cone like that, that would be not parallel to the base and it goes through the base. But maybe I could do one like this. That would also satisfy that requirement. Any guesses as to what shape we get this way?
A cone?
So keep in mind these slices are 2-dimensional, right? So we have a circle that's like flat, an oval that's flat. So we're not going to get a cone because that would mean like we're looking at a whole chunk of something, like something that has volume. But think about this rather like if you cut this, what does it look like on the flat edge that you cut it? And it turns out that this is indeed a parabola. Okay. So if you think about a parabola, kind of looks something like this, right? And there's not necessarily a piece here, but if we're going sort of up and around that cone like that, maybe we can see how that parabola follows like the outside part of the cone, right? And maybe in this slice up here, it's something kind of like that. All right, we've got one last conic section that we're going to focus on, and that is slices cut through both cones, and we end up with something like this. Right. This one is called a hyperbola, and it's going to looks very similar to the reciprocal function. What's the reciprocal function look like again? Anyone describe it, or maybe even draw right on my screen? I think you all have that ability. It is 1 over x, but what does it look like?
It has like 2 branches.
Beautiful. It has 2 branches, right? In fact, since I'm cutting through both cones, this first cut is going to give me like something like that up here. And then the second cone that it goes through, it'll give me like another one down here. Very, very similar to the 2 branches that we see in the reciprocal function. Okay. And actually, the reciprocal function is a very special case of a hyperbola. All right. Has anyone ever heard of the word hyperbole? Spelled very similar, but not quite the same as the word I've spelled up here.
Is it like an exaggeration?
Exactly, exactly. And so I do want to make that really clear for us here that this hyperbola is sort of, it's the one that looks like the reciprocal functions, whereas a hyperbole, we would say, is an exaggeration. Okay, so a little vocab for you today. Hyperbole is not the shape we're looking at. Rather, hyperbole is an exaggeration, and a hyperbola is the shape that we are looking at, right? So the only difference being that E on the end versus an A on the end changes the meaning of that word. All right, so let me just put this all on one screen for you before we move on. So we're looking at this, and the gist of what we're going to talk about today and on Monday is these different shapes and how we know from the equation what kind of shapes they're going to be, but also if we have a picture, how do we generate the equation? All right, so we're definitely going to be practicing going in both directions there. Now, before we actually get into an example, I want to take some time to talk about completing the square. Okay, so completing the square is something I had you look at in 15C, right? So the 15C class is meant to complement what we are doing in here. It might be asking you to practice some strategies that I know we're going to use a lot, right? It might be asking us to look ahead a little bit or review a little bit, but in this case, we were looking at completing the square as a way of factoring, okay? But the notion that I want us to do right here is make a note that when we're completing the square, our goal is to make a quadratic expression look like a perfect square. All right, we are trying to make a quadratic expression look like a perfect square. And what I mean by that is, let's say we had something like x squared plus 3, nope, x squared plus 6x plus 9. How would you write that as something squared?
X plus 3.
Nice. X plus 3 squared, right? Okay. So when I say the goal is to make a quadratic expression, so something with like an x squared and an x look like a perfect square, it means I want it to look like something squared. Okay. So let's practice this procedure. I know I had you look at it, maybe look up some different videos or, kind of practice that. But I think what's important is we sort of know A, what the process is, but B, like why that process works. Okay. So let's take a look at this first example. We have x squared plus 6x. The first question I want us to think about is, what perfect square does this look like? Right? The key here is it looks almost like a perfect square, but not quite. So what perfect square does x squared plus 6x look like? Or look close to? Give you a hint, it's already on the screen. Okay, great answer. So I added another question, right? What perfect square does this look like and what is it missing? And I think, Ian, you've answered both questions right there. Okay, so x squared plus 6x. We can say x squared plus 6x looks similar to x squared plus 6x plus 9, which is x plus 3 squared. But we are missing a plus 9, right? So x squared plus 6x, x squared plus 6x looks very close to this, except we don't have the 9, right? So if I add 9 to x squared plus 6x, I would have a perfect square. But I would also change the equation. I don't want to change the equation. So the second question I want us to ask ourselves is, how do we keep the expression equal to the original? All right, so if I write x squared plus 6x plus 9, all of a sudden I've changed my question because I had x squared plus 6x. What would I do to get back to x squared plus 6x with no 9?
Couldn't you throw it into an equation and then subtract 9 onto the other side?
Okay, well, I love the suggestion of subtracting 9, and we don't need to throw it into an equation to do that, right? So we have x squared plus 6x. I added 9 to make it a perfect square. But if I then subtract 9, don't the 9 and 9 go away, right? Then we have x squared plus 6, which is what we started with. So this part right here, this plus 9 minus 9, it makes the perfect square and it keeps our original equation or expression the way it is, okay? Instead of writing x squared plus 6x plus 9, I can write x plus 3 squared. That would give me x plus 3 squared minus 9. Right? Because this minus 9 that we used to balance everything out, we still have to write it there. So before we move on, can someone tell me how I can get from 6 to 3? Yeah, I could get from 6 to 3 by dividing by 2. Okay. All right. Let's try this with the second example. Okay. So here's my suggestion for this one. In the previous question, right? In the previous question, we were looking only at something that had a quadratic and a linear term. And so I want us to zoom in and focus on just the x squared minus 18x part, okay? And I want us to ask ourselves the same two questions. What perfect square does this look like and what is it missing? And after we identify that, how do we keep the expression equal to the original? So x squared minus 18x. What perfect square does that look similar to? Good. And before we get there, x squared minus 18x plus 81, which is x minus 9 squared. So x minus 9 squared is the same as that perfect square. And it's what x squared minus 18x looks most similar to. But we are missing, what are we missing this time? We're not missing a plus 9.
Plus 1.
We're not missing a plus 1. I'm asking us to compare x squared minus 18x to this thing in the green.
Oh, plus 81.
Yeah, we're missing a plus 81. Perfect. So if instead of x squared minus 18x, if I added 81 to make it a perfect square, what do I have to do to balance that out?
Don't you need to subtract 9 squared?
Okay, so we added 81 here. So in order to keep it balanced, we would need to subtract 81. Exactly. Right? Because 81 minus 81, that goes to 0. And then x squared minus 18x is what we had up here. Okay. The nice way about writing it this way is everything in this green can be replaced with a perfect square. And then I just have a minus 81 at the end. So x minus 9 squared minus 81. Right, this is our green, and the minus 81 that we put there to balance everything out is still there. Okay. Now, if we put this all back into the equation, we'll get x minus 9 squared minus 81 plus 80 equals 0. X minus 9 squared minus 1 equals 0. And if I were to solve this equation, I can actually solve this without foiling anything out, okay? I could add 1 to both sides. I could take the square root. What do I get when I take the square root of the right-hand side? I give you half credit for that. There we go. We'll give full credit to Matt. Dallas, you got half credit today, but that plus or minus, right? And I'm so glad that you said that because we all forget. We all forget as we're going through. We're like, like as soon as someone points it out, we're like, obviously it's plus minus, but I want us to get to the point where we're like, we know it's plus or minus and we have to consider both, right? So this gives us x minus 9 equals -1 or x minus 9 equals +1. And we'll get x equals, oh, how's my arithmetic this morning? -1 plus 9 gives me 8. And x equals 1 plus 9, which gives me 10. Okay. Now we could have factored from the beginning and solve this without using completing the square. But I think the part that I want us to practice is the completing the square part, okay? And the reason being, it's going to be very, very helpful for figuring out how do we sketch a quick graph if we can complete the square for conic sections, okay? All right. So let's level up. Let's get ourselves prepared for the kinds of questions we're going to be looking at today. All right. These kinds of questions are exactly what our let's graph something is going to look like. All right. Now, I'm going to spoil the surprise here, and I'm going to tell you that this is actually going to give you an ellipse. All right, I'm going to spoil that surprise. This is going to be an ellipse. If you're sitting there being like, how does she know that? That is the perfect question, because you too are also going to be able to tell from looking at an equation, oh, this is going to be this shape or it's going to be that shape, okay? So the reason why I had us practicing that completing the square is because in these conic section questions, oftentimes we have to complete the square not just one time, but 2 times in the same problem. Right? So if completing the square with one equation is tricky for us right now, that's a good indicator. I should probably spend some time practicing that skill so that when I need to complete the square for more than one variable in the same equation, that I feel comfortable doing that. Okay. All right. So here's what we're going to do. All right. We're going to take some terms and we're going to split them up. We're going to sort of sort them. All right. And the way that we're going to sort is we're going to collect all the terms that have an X. And then we are going to collect the terms that have a Y. And then anything that doesn't have either of those, we're going to say, hey, you, go sit on the other side just for a moment while I deal with the other things. Okay. So when we look at these things that look complicated, we're going to say, it's okay. It's going to be okay. Let's start by being mathematicians and saying, let's just collect all the things that are similar with each other, right? And so when I rewrite this, I'm going to get 16x squared plus 64x. And then separately, plus 9y squared minus 18y. And then that 71 that didn't have an x or y. I just want them to go sit in the other side for just a moment while we take care of the rest of the stuff. So get a plus 71 on that side. All right. So now we've gotten our lone constant on one side. We've clumped our y's so that they're sort of in the second half of this expression or this equation, and we've grouped our x's so that they're in the front part. Okay. Now I have been asking us to factor quite a bit, and again, not out of punishment. Nobody wants anybody to be more frustrated than they need, but simply because I know it's a tool that's going to come in really handy for us. And so I want us to feel comfortable saying, I have access to this tool, therefore I can answer these kinds of questions. All right. And what I'd like us to do right now is look for some greatest common factor. All right. And so I'm going to model the first one. For the ones in the light blue, I can, actually, let's not call this greatest common factor. We're just going to look for a common factor. And I'm going to go ahead and factor out the 16. And when I do that, I'm left with x squared plus 4x. Okay. Now, if you folks could do the same thing with the ones highlighted in the yellow. What do we get if we use that same idea with the yellow?
You could take out 9, get y squared minus 2y.
Good.
I guess you could also take out a y, but not.
Yeah, that would be the same thing I was thinking when I wrote greatest common factor, and then I took it back because we don't want the greatest one necessarily, but we would like to get that constant out if possible. Okay. All right. So now we're going to play complete the square twice. We're going to play complete the square once for the one in the light blue. Then we're going to play complete the square for the one in the yellow. All right. And so the blue part, x squared plus 4x plus what number would go here to make this a perfect square?
4.
Yeah, it would be a 4. Okay. Okay. Now, let's do the same thing with the yellow. Nine. I've got y squared minus 2y. What do I need at the end to make that a perfect square? Yeah, I'm gonna need a 1. Right, I'm gonna need a 1. Now, I argue that this last line that I've written here, the way it's written right now, is mathematically incorrect. There's one thing, actually, I would say maybe 2 things that I've done that make this line actually an entirely different problem than what I started with. That's a really good guess. I appreciate that. We haven't taken any square roots yet, so there's no, is that what you mean by the plus minus, or what are you referring to?
I guess I'm getting a little bit confused on how you take the completing the square, because normally I just leave like the +4 or the +1. I'll just leave it as like 2 squared and then like 1 squared.
Mhm.
And then so I guess with that, you could do both plus or minus.
Are you saying that like this is 2 squared?
Yeah.
And is your question, why is this a plus?
Not necessarily why that's a plus, because I know that we're like adding to it,
Mhm.
but like the way that I would write it is just keep it there, and then I'll just drop the x, drop the plus, and then drop the 2, and then make it into the square. So I'm kind of struggling following.
Okay, I see what you mean. I think once we sort of rewrite it, we'll get to where you're getting. But I would say that if we think back to like example 2, right? I made something into a perfect square, but then why did I put a minus 81 at the end?
To negate the addition that you did.
Yeah, I did that negative 81 to balance out this plus 81 that I introduced, right? Because if I don't have the orange part, I've actually changed the problem, right? Same thing up here. If I have x squared plus 6x and then I add 9, I'm changing the problem. So I gotta do a minus 9 to sort of keep it balanced, okay? When I added 4 over here, what did I add to the whole left-hand side?
Total, you added 5, I guess.
Just this 4. I added 4. Did I just add 4 one time?
No.
How many times did I add 4?
Wouldn't it be twice if you extracted the common factors? Like, shouldn't you add it back more?
You should add it back more. And I agree that it ties into the common factor. I added 4 on the inside of the parentheses, but it's really 16 of them, 16 4s. If I add 16 times 4 to the left-hand side, I better add 16 times 4 on the right-hand side. If I don't, then I've added more stuff and I've changed my equation. So in other words, it wouldn't be balanced anymore. What does that mean that this +1 in the yellow contributed? Because it used to be x squared minus 2y, and then I made it into x squared minus 2y plus 1, right? So this +1, yeah, I added 1, but I really added 9 ones. So on the right-hand side, I also have to balance out the changes that I made. Now I have made some perfect squares and I balanced them out. And since I balanced out the things that I added, everything is still the same. Okay. And now I think is maybe, Dallas, where you were looking in terms of like rewriting it as the perfect square. Okay. So this 16 stays as a 16, but instead of x squared plus 4x plus 4, I could write that as x plus 2 squared. And over here in the yellow, instead of 9 y squared minus 2y plus 1, I can write that as 9y minus 1 squared. And if I add up all the numbers I have on the right-hand side, I should end up with 144. Okay. We're going to go through this process a lot of times today. So we'll get more practice. You'll also have more practice on the quiz that's due on Friday to practice this process here. All right. But before we take our break, I want to simplify this a little bit more. And in particular, I want to make this right-hand side equal to 1. So tell me some ways that we can make the right-hand side equal to 1. Okay, I could divide by 144. Is there anything else that I could do? I could do minus 143. Yeah, for sure. Okay, so we have some options in terms of how we could make this right-hand side 1, but I will go with this suggestion here, the first one made by Dallas and Ian, that let's just divide by 144. Okay. And so if we divide by 144 by 144, we're going to have to divide everything by 144. So we're going to get 16x x plus 2 squared over 144 plus 9 y minus 1 squared over 144 equals 144 over 144, which we know is 1 because we wanted to make it that way. So now let's reduce. (144) divided by 144, that gives me 1 on the right-hand side. Tell me what this first fraction reduces to. Tell me what the second one reduces to. Nine on the bottom of the first one. I love that. And so we can actually reduce this to x plus 2 squared over 9. Perfect. 16 on the bottom of the second one. Perfect. Then we get y minus 1 squared over 16. All right. This right here is the pre-work that we're going to do for these problems so that we can get it to this form, because from this form, it's going to be really easy to graph. Okay. So with that being said, let's go ahead and take a break. All right, so it's a little bit on the earlier side, but I think that's okay. So it's 10:27 right now. Let's go until 10:37:43. Okay, so let's take a break until 10:43. And when we come back, we're going to take a look at how this whole example number 3 is going to be helpful in graphing the ellipses and circles that we're going to take a look at today. Okay, so I'll leave this up on the screen during break in case anybody wants to go back over it and look over it and think about like how we got from one step to another. All right, so I will see you folks back here in about 15 minutes. All right, so before the break, we took a look at conic sections, right? Thinking about, yes, it's this fancy word, but what does it actually mean? And today we are focusing on circles and ellipses, and we'll sort of save the parabolas and hyperbolas for next week, all right? We also reviewed this idea of completing the square, right? So thinking about what it means to complete the square, what that process is, and some of the steps along the way may look a little different for different people, but the flow of the process should be very similar, okay? The idea that we're trying to craft this perfect square, and once we have that perfect square, we want to keep things balanced. And so let's take a step back from the completing the square and just focus on this question, what do the equations tell us, okay? So let's take a look at this equation, all right? So we've got x plus 3 squared plus y minus 4 squared equals 36. And before we take a look at this specific question, I'm wondering if you can tell me, based off of what we learned about graph transformations, what does x plus 3, write this, what does y equals x plus 3 squared look like? Right, so we've talked a lot about graph transformations. Wanted to start the year with graph transformations because they come up again and again and again. And so if we just looked at this x plus 3 piece, would you know what shape that is? Just this.
A parabola?
Yeah, that would be a parabola, right? Facing up or facing down?
Up. Because it's positive.
Good. The parabola facing up. What does this x plus 3 tell us?
It moves to the left.
Yeah, it moves to the left 3. Exactly. Okay. So this right here is going to be important in unpacking what this slightly different equation tells us. Okay. So now Dallas is correct in the sense that this whole equation, the box, the general form of that one and shape is a circle. Okay. And so over here in this box to the right, we're going to write that it is a circle. And the reason why we know that, we're going to put the sort of general form with a lot of letters here, is going to be x minus h squared plus y minus k squared equals r squared. Okay. Here's what all of these things tell us. Okay. So the h and the k, they tell us where the center of the circle is. Now, if this x plus 3 that we talked about for the parabola moved the parabola to the left 3, that means that the vertex is at -3, right? Because we moved over to the left. What is the x coordinate of the center of our circle? Yeah, it's going to be a -3. Okay. What about the y coordinate of the center of the circle? Yeah, exactly. It's going to be 4. Okay. So one note that you might want to make for yourself is that we want to make sure that we switch the signs from the equation, right? This was a +3, but +3 means we move to the left 3. So that's why it's a -3. And this is a -4. So we switch that sign and make it a +4. Okay, so we found the center of our circle. And in fact, we could go ahead and plot this center at -3, 4. Now, every circle has a radius, right? And in fact, in our equation here, we have r squared on the right-hand side. And I bet if I gave you folks one guess, you would be like, r probably stands for radius, okay? Is the radius 36? That might be something that you take the time to rewrite so that you can see what the radius is. Okay. The easiest way, I think, to sort of draw your circle, all right? I want to be really upfront here. I am not here to judge the quality of anyone's drawings, okay? I mean, right now, the drawings that I'm making over here, technology is definitely my friend because I can make the tablet will turn things into straight lines for me, right? It'll draw a perfect circle for me. I'm not judging the quality of the drawing, but I do want to see those characteristics, okay? So when we draw a circle, we want to be able to see the center, and we also want to be able to see the radius. And I think the easiest way to do that is from your center, count out 6 units in the right direction, the up direction, the left direction, and the down direction. So from my center, if I count over 6 to the right, I'll end up here. If I count 6 up, I'll end up here. 6 to the left, 2, 4, 2, 3, 4, 5, 6. And if I count 6 down, 5, 6. Okay. For me, I find it easier to draw my circle if I have the outer parts of the circle sort of marked out. I think that point is actually incorrect. 1, 2, 3. 1, 2, 3. I think this one is actually incorrect. 1, 2, 3, 4, 5, 6. No, we're good. Okay. And then if you happen to have technology that allows you to draw a perfect circle, fine. Otherwise, I'll sort of mimic what mine will end up looking like if I did not. Right, mine was probably going to look more like a rounded square situation, right? That's a particularly bad one, not on purpose, but great example of like, you know, I'm not here to judge your drawings because mine are not perfect, right? So the important thing that I want to see here is you've got your center, -3, 4, and you can tell that the radius is 6, okay? So you might be asking yourself, well, how did she know that that was going to be a circle? And it turns out anytime you see an equation of this form, x minus a number squared plus y minus a number squared equals r squared, you're going to end up with a circle. Okay, so just as quickly as you were able to say, oh, y equals x plus 3 squared, that's a parabola. Now we're leveling up, we're adding to that. We're saying, oh, when we see something like this, we want to know that's a circle. Okay, and in fact, it gives us the center of the circle along with the radius. And so from there, we can draw our picture, not a problem at all. Now, you might be also thinking that this equation down here looks much more simple than the equation down here. But yesterday when we were looking at, or when you were looking at Desmos, the circles are sort of paired with the ellipses. And so what I want to do is very quickly show you how we could get from this version of the equation to one that looks more like this one, and think about how we can use that to tell whether we have an ellipse or a circle. Okay, so let me copy this equation down right here. I've got x plus 3 squared plus y minus 4 squared equals 36. And I'm going to ask you the same question I asked you when we had a 144 on the right-hand side. And that was, you have 144 on the right-hand side. How do you make that into 1? And people were like, well, you divide by 144, right? So if I ask you the same question here, how do you get the right-hand side to be 1? What would you say? Yeah, let's give that a try, right? Let's divide by 36. Now, if we're going to divide by 36, everything on the right-hand side gets divided by 36, but so does everything on the left-hand side. And so we'll end up with x plus 3 squared over 36 plus y minus 4 squared over 36 equals 1. All right, now I'm going to ask us to do even one more step. And that is, you notice how on the numerator I have like something squared? How could I write a similar structure on the bottom? Like if I didn't want to write 36, how else could I write it? Perfect, 6 squared. Okay, well, let me do the same thing for the second fraction. Y minus 4 squared over, oh, it's the same number, so it's just going to be 6 squared again. equals 1. Check out what this tells us. Oh. Still gives us the center, right? But look at what these numbers below do. Silly question. Is this pink 6 associated with the X or the Y? It's associated with the X. So guess what this 6 tells us? The 6 tells us how far we go side to side from the center. So the 6 is associated with the X, and X means side to side. So the 6 underneath the X tells us how far we go side to side from our center. Now I know we have the same number here, but the second 6 is associated with not X, right? In fact, this 6 is associated with the Y. What do you think the green 6 tells us?
Like how it expands vertically.
Exactly, exactly. So this green 6 is how far we go up and down from the center. How did we know that this second one tells us that we're going up and down from the center? Because it's with the Y, right? Okay, how did we know that this one tells us we're going side to side? It's the X above, right? So the letter, the variable in the numerator, that tells us more about what that number is going to tell us, okay? Okay, so we have a circle. Let's go back to this for a moment. We have our center. We switch the signs, right? -3, +4. We plot that center. From the center, I'm going to go 6 units side to side because the 6 is the number that's squared underneath the X. And so I count out 6 this way, I count out 6 this way, and I can mark those spots. Then I said, let's look at the fraction with the Y's. The number in the denominator that's being squared is 6. So that tells us how far from the center we go up or down. And because those numbers happen to be the same, 36 and 36, or 6 squared and 6 squared, we get a circle. Okay. But let's take a look at what happens when those numbers are not the same on the bottom. Example 5. I bet you can tell me what the center is. I bet you can tell me how far to go side to side from the center and how far you're going to go up and down from the center. What is our center?
-2, no, 2, -5.
Yes. And I love how you were like, oh, no, that's actually not it, right? So we want to switch the signs. And so sometimes, especially as I'm like starting to learn something, I'll make notes for myself so that I continue to remember what I should do instead of letting myself repeatedly make mistakes, right? So we switch the signs, we'll get a +2 and a -5, all right? Now, 4 and 9, what does the 4 tell us? It's the x distance, okay? And what specifically does it tell us to do from the center? Okay, so maybe we take a moment to write this as 2 squared, which means that we're going to go from the center, we're going to go 2 side to side, right? We have this, it's underneath the x, so that tells me I'm going side to side too. All right, what does this 9 tell us? Yeah, so wherever my center is, I'm going to go up 3 and down 3 from the center. Do we think we're going to get a circle? How could I change this equation so I do get a circle out? Yeah, if the 4 were a 9, perfect. And the other way around, right? If this is a 9, we have a circle. But if the first number is a 4 and the second number is a 4, then we have a circle. Okay, so here's my suggestion. With these kinds of problems, it can often feel like there's so much stuff to fill out. And so as soon as we get some points, I would say, go ahead and throw them on the graph. Draw your picture and then use your picture to answer all the other things. Okay. I've had students try and memorize things. That usually does not go really well, but the students who are like, okay, if I can do this, and then I can draw a picture, then I fill in all the other stuff, they tend to be a little bit more successful and the stuff tends to be a little bit more sticky, like they remember it better. Okay, so let's draw the center, 2, -5. So over 2, oh, down -5. There's my center. Okay, now from my center, I'm going to go out to the side 2 units because 2 squared was under the x. And from my center, I'm going to go up and down 3 units because 3 squared was under y. And then I'm going to do my best to connect these. Sometimes I cheat and I draw a top half and a bottom half. Okay, again, nobody's here to judge your drawings. Clearly mine is a lot lumpier than this beautiful picture that I copied and pasted from a textbook, right? But that's okay. My points mean the same things, and I got them very accurately from the equation. Okay, so these were the ones from the x. These are the ones from the y. Now, let me ask you a question. In your very professional opinion, do you think that the green dots are closer to the center than the pink dots? Or do you think the pink ones are closer to the center than the green ones? Yeah,
The
those
pink
pink
dots
ones.
are closer.
Exactly, right? What a silly question I would ask. Clearly we can count. We know this is 2 and 2 is smaller than 3, right? But you know what you just answered. The points that are further away from the center we call those the vertices. The ones that are further away from the center are the vertices. The ones that are closer to the center are the co-vertices. Okay. So we're going to learn a lot of vocabulary, and I think it can get very overwhelming. But if you can look at a picture and say, these ones are further away, those are your vertices. And if you can look at a picture and be like, oh, these ones are closer, those are your co-vertices. Okay. You know what those points are. It's more just connecting the language in your brain. Okay. So we're going to go back up here. Vertices, vertices, we're going to write further away from center. And the co-vertices will write closer to the center. Okay, so the ones that are further away and the ones that are closer. Now, in this case, the vertices were the green points because they're further away, not because they're green. Okay, because they're further away. Now, did you change the x coordinate or the y coordinate from the center? In other words, if we go back down to this diagram, we have our center point and then we have our vertices. Do those points have the same x value or the same y value? They have the same x. Okay, so that must mean that they have different y values, right? In fact, from here, what did you add to the y value to get the green vertex up here? We added 3. Okay, and how did we get from the center down here? We subtracted 3. Brilliant. Okay, so the textbooks sometimes will give you a formula, but I think when we get the formula, it sort of like ruins the surprise of why it is the way it is, right? But if we take what you just told me, we can figure out that formula. The vertices, we're going to keep the x value, right? Because we're looking at the green dots that are above and below. And we're going to take the y value of the center, -5, and we're going to add and subtract 3. 3, because that was the number underneath y. That will give us 2, -8 and 2, -2. And 2, -8 and 2, -2 should match with those green dots that we have below. Okay. All right. How could I write a similar equation to find the co-vertices? Good, good. Okay. So keep in mind that we have to keep the center, right? So we're going to have that 2, which is exactly what Ellie said. We have 2 and then plus or minus 2 because that was 2 squared was the number underneath the x. And so we'll get 2 plus or minus 2, comma, negative 5. And we'll get 0, comma, negative 5. And we'll get 4, comma, negative 5. And I bet you that that should match with the pink dots that we have below. Okay. So textbooks and websites and videos will give you all sorts of formulas, and there's nothing wrong with having a formula. If you have amazing memory and you can remember that formula forever and ever, perfect, great, right? I'm not like that. It's harder for me to remember things, especially if I don't really know like where they're coming from. And so for me, if I can draw the picture, then I can get the information from the picture. It's like maybe like a cheat code for myself. Like that's how my brain works. So I'm going to make sure that I do something that is efficient for my brain. Okay. I want to make a couple notes about the vertices and the co-vertices. The vertices will be the square come from the square root of the bigger denominator. Okay, they come from the square root of the bigger denominator. So whichever points are further away, those are the ones that are the vertices. In contrast, the co-vertices come from the square root of the smaller denominator. Okay, because the co-vertices, doesn't matter whether they're side by side or up and down, they come from the smaller denominator. Okay. The center, if we were to leave ourselves a little note here, the center comes from h comma k, and probably worth writing, don't forget to switch signs. Right? If I were making a reference sheet for next week, I think maybe writing this down would be helpful. But if I know I make these mistakes, it might be super helpful to even write switch the sign so I don't forget, right? All right, the general form here. So when the two numbers on the bottom are different, we end up with an ellipse. And you folks did a great job earlier of saying, this is how I would make it a circle, right? You would make the numbers the same on the bottom. But the general form will be something like this: x minus h squared over some number squared. Plus, and wow, that plus sign is going to be so important for us, okay? Plus y minus k squared over b squared equals 1. And so if we see an equation in this form, or we can make it look like that form, then we're going to have an ellipse. All right. Now, one of the slides in that Desmos activity, and someone brought this question up earlier, and I was so grateful for this question because I think it's a fabulous question. In one of the last slides, there was like an animated one where there was like the 2 points in here, and then it's sort of like connected like that. And then this point moved around the ellipse. Does everybody know which one I'm talking about? All right, so it was these 2 points in here, and then it sort of was like, oh, like that length stays the same, but then as I move this around, like if I have a string tied to those points, I move it around, I end up with an ellipse. Okay. So there's two important points that we still need to find. We have our vertices, we have our co-vertices, and in a circle, we only have a center. But in the ellipse, we have these points that are inside of the ellipse that are called foci. Okay. I usually mark these with an X when I'm drawing my diagram, so I know they're different from the other ones. But as you're drawing your graphs, you should make sure that you have the foci there, okay? The foci are always in the same direction as the vertices. Okay, the foci are in the same direction as the vertices. In fact, there's so many special points along this line, like we have the vertices and the foci and the center, that we call this line the major axis. All right, so the major axis goes through the vertices, the foci, and the center. So many points, we call it the major one. The shorter one, we just call that a minor one. Like it's not as major, right? Like Major League Baseball, minor league baseball. All right. Let's talk about A, B, and C though. All right. So A, B, and C was something that you saw in your Desmos activity, right? And they gave you some equations with it. And I love that people were like, I don't know where these came from, because that is precisely the point, right? Sometimes textbooks or resources are like, bam, here's an equation, do it. And you're like, I don't know why, right? And we should, as skeptical mathematicians, always be wondering, but why is this the case? So here's what A, B, and C look like geometrically, okay? I'm going to use this prettier diagram to show the A, B, and C, all right? This distance, so all the way up to the vertex, down to the center, that is A. All right, so A is the distance from center to vertex. Okay. B is the distance from center to co-vertex. So like from the center to the co-vertex, that would be B. C is the distance from center to a focus or one of the X marks. So this is C. All right. This is one of the rare cases where it's okay to say, this diagram is drawn to scale. We have A, we have B, and we have C. Which one of these is the longest? Yeah, A is the longest, right? Because A goes all the way from the center to the vertex. C only goes up to this point, and then B was defined to be the shorter one. So A is the longest one right now. And it turns out that B is here, C is here, but if I connect that to make a, what kind of shape am I making right here? Right triangle, okay? If I make this into a right triangle, B and C are the legs of that right triangle. Cleverly enough, this hypotenuse, that length is A. Here's how we're going to generalize this for ourselves. The bigger denominator, which in this case was A squared, is equal to the smaller denominator plus C squared. I'm saying that the smaller denominator, B squared, plus C squared, because it's a right triangle, will give me A squared. And C helps us find the foci. All right. So let's practice this with the numbers that we had from here. All right. Let's go back up to the equation for a moment. And if I want to write this equation with the numbers that I'm given there, the bigger denominator is 9. So I'm going to write 9 equals, right? So bigger denominator equals 9 equals. What does it equal? The smaller denominator, which is 4, plus C squared. I don't know what that is, but we're going to find it. So 9 equals 4 plus C squared. How do we solve for C squared? Or how do we solve for C? We're going to minus 4 from both sides precisely. So 5 equals C squared. Root both sides. We get C equals plus or minus root 5. All right. And we don't want to turn that into a decimal. In fact, we're going to embrace this, the beauty in the exact value. Square root of 5, lengthy decimal that doesn't terminate. We're going to keep it as square root of 5 and just enjoy it. Where do I add or subtract this square root of 5 from the center? Do I add it to the x values or do I add it to the y values? Yeah, how did you know that? Why are we adding it to the y values?
Because the major axis is vertical.
Mm-hmm. Yeah, so our one focus might be somewhere here, the other one might be somewhere here, right? So just like the vertices, we're changing the y value, so we're going to add it to the y value. And so when we do that, we'll get 2, -5 plus or minus square root of 5. And since I am asking you to graph, it might be nice to turn it into a decimal just for graphing purposes. And I believe we get 2, -7.2 and 2, -2.7. And so we can graph these on here. Negative 7.2 will be somewhere around here. Negative 2.7 will be somewhere there. Okay. And so we have a fully precise diagram here. It's got a center, it's got the vertices, the co-vertices, and the foci are marked and they're on the same axis. In fact, we call that the major axis with the vertices. Okay. Let me ask you some what if questions. All right. I like what if questions because instead of having to go through an entire other example, I mean, we'll go through some examples, but it gives us a way to think about how things change and how to sort of almost prepare for other scenarios. Okay. So let's say that I had this. X minus 2 squared over 9 plus y plus 5 squared over 4 equals 0. How would that change my picture? Let's start there. How would that change my picture?
It would change the major axis to be horizontal, so on the x-axis.
Mm-hmm. Yeah, I agree. In fact, we might even think that our ellipse will be more like this way. Would I still add or subtract values from the y coordinate to find the vertices? No. Because if I have an ellipse that's this way, my vertices are going to be in the x direction. So I would have to add those to the x direction. Okay. The co-vertices would be like here and here. So I would add those to the y coordinate. All right. So there's a lot of decision making that we really need to do. We can't just autopilot, like copy formulas and hope that we're just going to get what we get. And I think sort of the way to avoid that panic, plug things into a formula, is to get your picture down as soon as you can. Because if you can do the picture, and I know you can all count and see which one is longer than which one, I think you give yourself so much more access to the problem. Okay. So before we move on, all right, we're going to move on. We're going to do a few more examples. I'd like to take a quick 5-minute break. All right. I know that the classes are long and we took our break a little earlier than normal today. So let's take a quick 5-minute break. Let's be back at 11:35 a.m. And then we will move through as many examples as time allows in the rest of this section. Okay. So I'll see you folks back here in about 5 minutes. Recording. All right, so let's take a look at example 6, all right? And I know we've just learned quite a bit of stuff, but my hope is that this equation actually looks pretty familiar to us, okay? In fact, there's a box below the equation that says complete the square, right? And if we look very carefully at the numbers, it turns out that this is the exact same equation we did the very beginning when we were practicing completing the square. And so I'm going to cheat here because I can copy and paste. I'm going to scroll back up, copy and paste that complete the square right in here. All right. Boop, boop, boop. All right. So here's our complete the square, same numbers. So I'm going to go ahead and grab this, duplicate it. Oh no. I'm going to duplicate it, scroll back down. Paste it right in that box that says complete the square. Looks like we need to shrink it just a little bit. All right. So we see this equation. Our first instinct should not be to panic, but it should be to confidently say, I'm going to complete the square. I'm going to complete the square for the x's, also for the y's, and I'm going to get this into a form that is going to make it easy for me to tell what shape it is and how to graph that shape. Okay, so based on this equation now, tell me what shape it is. Bingo. We have an ellipse, right? And if this were a 9 and the second number were also a 9, we would not have an ellipse, but we would have
A circle.
we would have a circle, right? So similar. This plus sign though, that better be a plus. If that's not a plus sign, we're gonna get a different shape, okay? So let's take a moment, rewrite this in a way that might be more useful for us. In particular, x plus 2 squared over something plus y minus 1 squared over something else equals 1. What are we going to put in the denominators for each one?
Uh, 3 squared and then 4 squared.
Bingo, 3 squared and 4 squared. Perfect. All right, I'll give you a moment to write out your center, maybe sketch a graph. And if you get that far, think about how you're going to find the vertices and how you're going to find the co-vertices. Okay, let's take maybe about 2 minutes, write down what we can, start to sketch out what we can. All right, for our center, what would be the wrong answer? Let's start there. What would be the wrong answer? Good. 2 comma negative 1. Very much the wrong answer. But we would catch that, right? We would make sure, oh, we got to switch the signs. -2 comma +1, right? So I can plot that right away. -2 comma +1. I've got that center. And from my center, tell me how to get to the vertices.
Up and down 4.
Up and down 4, right? And so if I wanted to write that here, I would say keep the x, but the y value, I'm going to go up or down 4, right? That's what it means when we write plus or minus 4. So I'm going to go up 4. I'm going to go down 4. Those are my vertices. All right. How do I get to my co-vertices?
Left and right 3.
Yeah, 1, 2, 3, 1, 2, 3. And I can write this as the x value. I go right or left 3. That's that plus or minus 3. But the y value of the center stays the same. Okay. And so we can carefully connect these right? Doesn't have to be perfect. But we end up with an ellipse here. Now we are not done though. We do want to make sure we get our foci in there. And so are the foci going to be side to side from the center, or are they going to be up and down from the center? Yeah, up and down, which means that I'm going to have to do something like this where I add to the y values, okay? But if we were to set up an equation here to help us find out exactly how far, what number would we put on the left-hand side of this equation?
You do 4 squared.
Good, so I've got 4 squared equals, because that's the bigger denominator, equals 3 squared, which is the smaller denominator, plus c squared. And c is going to tell me how far I have to go up and down from my center. Right. So 4 squared is 16 minus 9, that gives me 7 equals c squared. So c equals plus or minus square root of 7. Now I chose this to be a square root of not a nice number because A, I want us to get used to things not always being perfect squares. But B, I think it's important to know, like, it doesn't mean you're wrong. If you get a square root, like a weird square root, it doesn't mean you're wrong. Okay, I think it's just that sort of earlier in your math career, it's more straightforward if we can have all whole numbers, but it doesn't have to always be that way. And so if I wanted to write my foci, I would say -2 and then comma +1 plus or minus square root of 7. All right. I think that works out to be somewhere right around here and somewhere right around here. Okay. But now we have our complete diagram. All right, we've got our vertices, our co-vertices, and our foci and our center. All right. Are there any questions before we move on? How are we doing out there in the cyber world? All right. Before we move to the next slide or the next page, how many folks here watched this television program growing up at some point? Anybody else? Yeah, it tends to be a fairly common show. And even if we have not watched it, we might be familiar with some of the characters on it. Anybody have any favorite Sesame Street characters? The Grouch. Oscar. Oh, Oscar. I like his little worm friend too. Cookie Monster is pretty good. I feel like these ones are like less known. Yeah, Big Bird, but isn't there the one with like the 2 purple monsters that are like stuck together? Or am I thinking of a different show?
I mean, I think there's 2 brothers, but I don't think they're stuck together.
Okay, it's been a while. Yeah. Well, Big Bird, Snuffleupagus, right? So like all of these characters on these shows. But what I really appreciate is that our friends Ernie and Burt can help us visualize ellipses a little bit better. Okay. And so in particular, we've been looking, the ones that we've drawn happen to look like this. All right. In that they're sort of like taller than they are wide. And so, you know, I like to connect things, new things that I'm learning to things I already know. And so I tend to refer to these kinds of ellipses as Burt ellipses because they're longer, just like Burt's head is longer and he's got the vertical stripe situation going on in his shirt, right? So it's like longer than it is wide. But then we have Ernie over here. And Ernie's head is sort of a little bit wider than it is tall, right? And so sometimes when we're talking about ellipses, it's useful to know, like, sometimes they're going to be wider, sometimes they're going to be taller. And you'll just maybe hear me refer to them as Ernie ellipse versus Burt ellipse. These are in no way technical math terms. So if you walk up to someone else and you're like, oh yes, this Burt ellipse, like no one else will know what you're talking about, then that's okay. So, just know that it's not a formal thing, right? It's just something that I think makes it a little bit easier for me to remember. But in this Ernie ellipse, I'm wondering if you can tell me where the vertices are. Yeah, the vertices are like where his ears are, right? Because they have a further distance from the center. That's it. All right, what about Burt? The Burt ellipses, where are the vertices there?
Up and down.
Up and down, right? So they're not Burt's ears like they are Ernie's ears. In fact, maybe they're more like his tuft of hair at the top and his chin, right? But the defining characteristic is that they are further away from the center. That's it. Now, I know that I've made us think through a lot of like, how do we get these formulas? And these formulas have kind of been on the page all along, but I've like made us think about how we get to them. I think that's a useful exercise. And I know some of us very much like formulas. So if you like formulas, here's a little blurb with formulas that you can use to kind of think about how you're going to find the different points of interest, okay? And I will say that sometimes it gets confusing because they use the same letters in different places. And so the way that this particular textbook works, the A, they're assuming that A is always bigger than B. They're assuming that A is always bigger than B, which means that this first ellipse is an Ernie ellipse because the bigger number's underneath the X. But the second one would be a Burt ellipse because the bigger number is underneath the Y. All right. And for this reason, that different textbooks label things differently, I find it really helpful for like students to just draw the picture and worry about, is it bigger or smaller rather than is it A or B? Okay. Anyway, that is there for your reference if you want. But what I would like us to do is maybe take a very quick look at example 7, but really skip down to maybe number 9, okay? So we'll very quickly look at 7 and 8, but then really focus our time on 9. Okay, so we've got this right here. Take a moment, read the equation. Tell me some things that you know.
It's a circle.
It is a circle. Excellent. How do you know that?
Because the denominator is the same.
Perfect. Because 49 equals 49. Love it. All right. What else do we know, folks? The center point is 2, -3. Beautiful. Change the sign of the -2, change the sign of the +3, and we've got our center. All right. If we have a circle, what other information do we need before we can graph this circle? Radius equals 7, perfect. So maybe we just sneak that in here, radius equals 7, and then we could just sketch a quick graph of this, right? So we're gonna go to 2, comma, -3. We're gonna count out 7, so 7, 7, 7, 7, right? And we connect everything with a circle. And again, I'm not here to judge you on the quality of this, though I think some of you in here are probably, enjoy being organized and making sure that your graphs are really pretty, right? And you don't spend too much time making it perfect, but something like this would be absolutely sufficient, okay? All right, so we've got our circle right here. And if it is a circle, we do not need to answer those other questions, okay? So we only need to identify vertices and co-vertices when it's an ellipse, not when it's a circle. All right, talk to me about example 8. Take a look at that equation. What are some things that we know?
It's an ellipse.
It is an ellipse, and how do you know that?
A and B are different. I mean, the denominator is different.
Perfect, I love that. 36 is not equal to 81. Beautiful. I wrote that in the wrong box. All right, center point. All right, we're going to change the sign. So not +2, but -2, not +1, but -1. Beautiful. And we could even plot that right away if we wanted to. All right, y-axis is the major axis. How do we know that? You are absolutely correct.
Because the 81 is under the y and it's bigger than 36.
Good. We want the bigger number, right? The bigger number tells us where the vertices are. So I would go from my center. I'm going to go up and down 9 to get to my vertices. So I count down 9. I count up 9. All right. My co-vertices from my center, I'm going to go to the right and left 6 and keep the y value the same. 2, 4, 6. 1, whoops. 1, 2, 3, 4, 5, 6. And so if we connect all of these, my ellipses always end up being like lumpier on the bottom, but good enough. All right. All right. Tell me what equation we use for the foci. What equals what plus what?
You do 81 equals 36 plus c squared.
Good. We take the bigger denominator. No matter how much bigger, only a little bit or a lot of bit, we put that on one side by itself. The other denominator gets added to c squared because that is the shorter leg of the triangle squared. We do some computations. I believe that c squared equals 45. C equals plus or minus square root of 45. And we can write our foci as, do I add this square root of 45 to the x value or the y value? That y value, right? So -2, -1 plus or minus root 45. And I believe that ends up being like we're adding about 6.7 to something. So 1, 2, 3, 4, 5, 6.7. 1, 2, 3, 4, 5, 6.7. All right. So not so bad when it's actually in this form, even though it has two fractions and a lot of squares going on. It's a very valuable format because it tells us so many things. Okay. All right. So let's take a look at one now where we have to complete the square. Okay, I want to practice the completing the square part, and I'll leave the rest of it for you to graph on your own. But I think it's valuable that we practice that completing the square once more before we leave here today. Okay. So what would be the first thing I would want to do when I look at this long equation? 4x squared plus 9y squared minus 40x, blah, 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 blah. Yeah. Let's clump things together, right? Let's take all of our x's and we'll clump those together. We're going to take the y's and we're going to clump those together. What do we do about our friend that has neither an x or a y? We're going to move that to the other side, right? Think of it as a little timeout situation, not because the 100 has been misbehaving, but sometimes it's easier to focus on what you want to focus on if there's not extra stuff happening there, right? So we clump, very official mathematical term. We clump our 4x squared minus 40x plus 9y squared plus 36y equals, don't forget to move that 100, and then it's, since it's a plus 100 on the left, we subtract it to move it to the other side. Great. All right, what do we do next?
Then you want to do the common factor.
Nice. And we leave that G off the GCF because this doesn't include the variables, but it's just actually looking at the numbers, right? So for the x's, I can factor out a 4, x squared minus 10x plus, what does the y term look like?
Be 9 parentheses y squared plus 4y parenthesis.
Perfect. All right. So we've got our 3 different pieces that are clumped by term type. And now is when we're like, let's make some perfect squares. And as we make those perfect squares, we need to be really careful to balance things on the other side, right? We don't want to create an entirely different equation. We want to keep it balanced, keep it the way it is, except in a more useful form so that we can graph it. All right. I think someone mentioned this earlier, but I just want to make this very explicit. All right. Some of us might be like, how are people figuring out that perfect square so quickly? And to answer that question, we consider the linear term. Okay, so x squared minus 10x. What's half of 10? 5. Okay. What's 5 squared? Perfect. That's how I get that last number. I take the linear term, the coefficient, I cut it in half, and then I square it. So 10 divided by 2 gives me 5. 5 squared gives me 25. plus, let's try that same thing over here. I already have y squared plus 4y. So what's half of 4? 2. And what's 2 squared? 4. Good. Okay. So we get half of that y value, or the linear term. So 2. 2 squared gives us 4. Now we've got not 1, but 2 perfect squares going on, which is exactly what we want. We want perfect squares. But in creating these perfect squares, we accidentally unbalanced our equation. So we need to come back in and rebalance the equation. Okay. I didn't just add 25 here. How many 25s did I add?
425.
I added 4 of them. Good. And how many 4s did I add?
9.
Good. Oh, beautiful. Okay. You have now balanced out your equation. All right. We've made it messier. Now let's pack it all back in so we can see those perfect squares. And we get 4, parentheses, x minus 5 squared plus 9 parentheses y plus 2 squared equals 36. All right. What is my last step here to make sure that I can see exactly what the graph is going to look like? Bingo. We're going to divide by that 36. All right. So 4 x minus 5 squared over 36 plus 9 y plus 2 squared over 36 equals 36 over 36. And we simplify. X minus 5 squared over what goes in the bottom? 9. Okay. And how might I be clever and rewrite that 9 so I'm already prepared to graph? Bingo. 3 squared. All right. And the second fraction, y plus 2 squared over, 9 and 36. I'll get a 4 down here, but to be clever, I make it a 2 squared equals 1. All right. So that, my friends, is the completing the square portion. And I'll leave the graphing part up to you. Okay, I did want to go through the completing the square at least one more time before I send you off. All right. But this is a good chance to practice. I bet most of us are probably feeling pretty good about the center, the vertices, the co-vertices, and the graph. I would encourage you to make sure you also feel good about finding the foci. Okay. All right. So we are going to finish off today with 3 questions that sort of ask us to go back in the other direction. All right. I think it's important to know how to graph. It's important to know how to complete the square, but we also want to say, if these are some coordinates, what does the equation look like? Okay. And so let's take a look at these last few examples. All right. So for examples 10 through 14, we're going to find an equation for an ellipse that has its center at the origin and satisfies the different conditions. So before we jump into that, earlier, I said x minus h squared over a squared plus y minus k squared over b squared equals 1 is like a general form of an ellipse. Meaning, if I want you to write an equation, you would be writing something like this, right? But I gave you a specific constraint in here that actually allows you to simplify this equation. How can I simplify this equation given the instructions for this particular set of examples? I argue that we're not going to need to fill in every single one of these numbers in the sense that we can already replace some of these variables with numbers. Tell me more about that, Matt. What do you mean by remove H and K? Yeah, how come we can put zeros for H and K?
Is it because the center is at the origin?
Exactly, exactly. When I said the center's at the origin, sneaky me was saying H comma K. Oh, let's write that more carefully, Judy. H comma K is 0, comma 0, right? Which means this is 0, this is 0. So really what I'm asking you to write is something that looks like this: x squared over a squared plus y squared over b squared equals 1. And to write that, we just need to find what is A and what is B. That's really all we're asking you to do. Find your A, find your B. Okay. So let's give that a try, okay? Example 10, we have vertices at plus or minus 8 comma 0 and foci at plus or minus 5 comma 0. Well, that to me is numbers, but if I could turn it into a picture, it doesn't have to be perfect. It can be a very quick sketch, but if I draw a picture, it might help me figure out if I have my A, if I have my B, or how I find those, okay? My vertices, positive 8 comma 0, negative 8 comma 0. My foci, 5 comma 0, negative 5 comma 0. Is this going to be an Ernie ellipse or a Burt ellipse?
Ernie?
Yeah, this is going to be an Ernie one, right? And so even though I don't know exactly what it looks like, I can sort of sketch one and say, oh, it's going to be something kind of like this. Okay, if I know it's an Ernie one, I have my major axis. I also, do I have A or do I have B given my diagram right now? Why do we have A?
Because it's on the x-axis, the major axis.
Exactly. Here's my center. I'm going out 8 units, and I'm going out 8 units. I'm going out 8 units side to side, so it's the number underneath x squared. So I already have x squared over 8 squared. I already have my a. If I could only find how far I go up and down from the center, then I could finish my equation, right? How do I find out how far I go up and down?
You could do the Pythagorean Theorem setup that you showed earlier.
So to find b squared, we can say the bigger denominator equals b squared plus, what's c squared? Five squared. Nice, nice. When we have information about the foci, that tells us our C. Okay. All right. 64 equals b squared plus 25. B squared equals 39. So b equals plus or minus square root of 39. What number do I put under y squared? Yeah. We're going to put a 39 because we secretly have square root of 39 squared, right? So we might even write, this would be perfectly fine to write as an answer, or you could write x squared over 64 plus y squared over 39 equals 1. Either one of those would be okay. Right? So very puzzle-like, right? Because I'm not saying giving you very specific directions. We have to make decisions along the way about how to find out the information that you want to find out. Okay. All right. Let's take a look at example 11. All right, I'll give you a moment to read that over. Maybe sketch a picture for yourself about what that looks like and what information we have. I know I'm definitely going to draw a picture, so I'm going to set up my XY coordinate right now while you folks are thinking. I'm even going to set up my answer, x squared over something plus y squared over something else equals 1. All right. What can I draw? Or what do I know?
You can draw the vertices on the y-axis, up 5 and down 5.
Good. 0, 5, 0, -5. And is this going to be an Ernie situation or a Burt situation? Yeah, we're going to have a Burt situation here. So again, I don't know exactly what it looks like, but I can draw something that is taller than it is wide. Okay. I can actually fill in one of the denominators as well, just from my diagram right now. Which denominator can I fill in and what is it?
Y 5 squared.
Yeah, 5 squared because 0, comma 5, 0, comma -5 means from my center, I go up and down 5 to get to the vertices, okay? Now, the number under x squared, is that gonna be bigger or smaller than 5 squared? It's gonna be smaller. Why is it gonna be smaller?
Because the vertices are on the y-axis, so therefore the minor axis is going to be on the x-axis.
Yeah. The vertices tell you about the major axis, but the minor axis is the shorter one, okay? Now I want to be really careful here about our language. So when I say major axis, I would tell you that the major axis has a length of 10. How many people here thought I was going to say 5? The major axis has a length of 10. It has a length of 10 because it goes from one vertex all the way to the other vertex. We measure the minor axis in the same way. This whole distance is the minor axis length. What are these coordinates?
Plus or minus 1.5, comma 0.
Good. Good. Okay, so when we talk about axis length, it turns out that the axis length actually is twice the distance that you have from the center to a vertex or a co-vertex, okay? So what number then would we put down here? Because I would not want to put 3 squared. Yeah, I'd want to put 1.5 squared or 3/2 squared. Okay. And that, absolutely fine. Okay, if you want to expand this a little bit, you could do x squared over, I think this turns out to be 2.25 plus y squared over 25 equals 1. But there's nothing wrong with leaving it like this. Okay. All right, let's take a look at number 12 here. Each one of these gives you different kinds of clues, all right? And again, I know at least for me, I'm a very visual learner. And so I already know that I'm gonna wanna draw a diagram. But we draw this diagram. I'll give you a moment to kind of sketch it out and see if you can fill in any of these numbers, either the A or the B that we need for our equation. All right, if I start to draw some of these things, I know the foci are like 3, 0, -3, 0. Is this going to be an Ernie ellipse or a Burt ellipse?
I forgot the names of them, but it's going to be longer horizontally.
Exactly. We're just going to have something kind of like this. Again, I don't know exactly how ovally my oval is, but the foci are in the same major axis as the vertices, so I know they go in that direction. All right, what does this tell us, this minor axis length? What does that tell us?
It tells us the co-vertex are plus and minus 1 on the y-axis.
Good. It might be so tempting to say plus or minus 2, right? I could totally see someone thinking, oh, it's plus or minus 2. But remember, the minor axis length means the whole thing from co-vertex to co-vertex is 2. So if I only want from the center to one of the co-vertices, it's going to have to be cut in half. That means underneath y squared, I can go ahead and put a 1 squared. All right. How am I going to find that number underneath x squared?
You could do a squared equals 1 squared plus 3 squared.
Can someone else explain to me why our a is on this side? Like, how come I didn't put it on this side?
Because A is bigger.
And how do you know that a is bigger?
Because it's longer horizontally.
Because it's longer horizontally. Perfect, perfect. So a squared is, let's see, 1 plus 9 is 10. So a equals the square root of 10. And so you have a couple options. You can write this as square root of 10 squared, or you can say x squared over 10 plus y squared equals 1. Right? Either version would be fine. All right, I want to go ahead and do one more example. We're going to take a look at example 13, again, just for some other vocabulary. We're going to talk very briefly about quiz 9 that's due on Friday, and then we will call it a day. Okay, so we're going to take a look at one more example, take a look at the quiz real quick, and then call it a day. All right, so example 13, a brand new word, eccentricity. Eccentricity is a description of how ovally the ellipse is. Okay, how ovally the ellipse is. Smaller eccentricity means more ovally. Eccentricity of 1 means it is a circle. Okay. So 1, if we have an eccentricity of 1, we're gonna have a circle. Okay, but smaller eccentricities are gonna mean more ovally in one direction, and bigger ones are also gonna be more ovally, but in the other direction. Okay, I'm not so concerned about that. as I think it's interesting to know that the eccentricity of 1 means that we're going to have a circle. Okay. Now, eccentricity is the ratio of C over A. But that means in this case, maybe C was 3, maybe A was 4. What are some other possible values of C and A? What else could C and A be?
Could it be the squared versions of them?
Like 9 over 16?
Yeah.
Let's see, does 9 over 16 reduce to 3 over 4?
Yes. No.
Which one is it?
No.
Yeah, that one doesn't reduce, right? But what else could we write to get something that still has the same ratio? Yeah, 9 over 12. That's another possibility, right? Maybe I had 6 over 8. I don't know, right? But all of these are possibles, right? So the eccentricity is usually the most reduced fraction, but we don't know what the fraction originally could have been. So C might be 3, but C could also be 9 or 6. And then A might have been 4, but it could also be 12 or 8. So to answer the question, we're going to draw a picture. Surprise, surprise. So if I sketch a quick picture, all right, and I think about the other piece of information I'm given, the vertices. The vertices are at 0 plus or minus 4. So here and here. Gonna have one that's kind of taller than it is wide. I argue that we have one of these values already. What value do we have already? Mhm.
It'd be 5 squared. I meant 4 square, my bad.
4, okay, I was like, I don't see any 5s. I know it's been a long class, but yeah, the 4 squared. In fact, the 4 squared is going to go under y because we're going up and down 4. Right? Now 4 squared is going to be the bigger denominator. But if 4 is that eccentricity, 3 must be our C value. And so we're going to get 4 squared equals 3 squared plus the number under x squared. And we'll get 16 minus 9 is 7 equals a squared, or the number underneath x will be square root of 7 squared. All right. So it can get confusing because sometimes A is defined as like the biggest one, and sometimes A is the one under X, depending on which version you look at. So again, I would encourage you, don't fixate on the actual letters. I would think about, is it bigger? Is it smaller? And that will take you so much further than like, is it A or is it B? Okay. All right, so I'm going to stop the video right there.